In this video tutorial, we will look at titrations involving weak acids and bases. So if you recall, titrations are a laboratory method used to indirectly determine the concentration of a solution by reacting with another solution, also known as a titrant, of a known concentration. So what does it mean to indirectly measure something? Well, let's pretend. Let's pretend there's a very, very small tunnel, and inside the small tunnel are holes in the ground. But I don't know how many holes there are inside the tunnel, and I can't fit inside the tunnel itself. So what I'm going to do is I will roll some marbles into the tunnel, and if it does not come out the other side, I can assume the marble fell into the hole. So I continue doing this, throwing marbles into the tunnel and waiting for it to come out the other side. If marble number 7 comes out the other side of the tunnel, how many holes were inside this tunnel? There must have been 6. Alright, so if marble number 7 comes out, then I can assume that each of these holes was filled with a marble, allowing my marble to roll through the tunnel, and therefore there must have been 6 holes. So was I actually measuring or counting the number of holes? No, I was counting the number of marbles. But because I know the relationship of marbles to holes is a 1-to-1 relationship, by counting the number of marbles, I've actually counted the number of holes. So we have indirectly measured one thing by directly measuring something else. Similarly, in this chemical reaction over here, I'm using hydrochloric acid to neutralize magnesium hydroxide base. All right? So how many HCl can each molecule of magnesium hydroxide neutralize? So for every 1 magnesium hydroxide, how many hydrochloric acids will it neutralize? So because it's a 1-to-2 ratio, 1 magnesium hydroxide can neutralize 2 hydrochloric acids. So remember, the ratio won't always be 1-to-1. Maybe in a different case, you require 3 marbles to fill up 1 hole. Then it'd be a 3-to-1 ratio. But so long as you know how much of one chemical was used, you can stoichiometrically calculate the quantity of unknown that was neutralized. Now, in the example of the tunnel and the holes, it's very easy to know when you've filled up all the holes because a marble rolls out. But how do you know when a solution has been neutralized? Well, we use acid-base indicators. Chemicals that behave differently depending on how acidic or basic the environment is. This is the molecule phenolphthalein. In an acidic environment, you'll have lots of H+ ions floating around in solution, and these H+ ions are attracted to the O8 or the C double bond O group over here, turning it into this hydroxyl group instead. A small change to the molecular structure here results in a cascade of structural changes here, turning it into this. And these changes causes light to refract differently, making this molecule colorless, while this molecule pink. Meanwhile, the opposite is true. If you're in a basic solution with lots of hydroxyl groups floating around, these hydroxyl groups will attract this hydrogen over here and rip it out towards the hydroxyl groups, and again, that conformational change results in this structure. And that is how our indicators tell us whether the solution is acidic or basic. So let's go over a sample titration. In grade 11 chemistry, you were asked to titrate an unknown HCl concentration using a known sodium hydroxide solution. The sodium hydroxide solution was known because you made it, so if you made it, of course you knew what the concentration was, and we gave you an unknown HCl where you didn't know how much HCl molecules were floating around the solution. Now from the balanced equation, we know it's a 1-to-1 ratio, so 1 sodium hydroxide is able to neutralize 1 hydrochloric acid molecule. So right now the indicator, phenolphthalein was the example we used, is colorless because right now there's a lot of H+ ions floating around the solution. If I add a sodium hydroxide to it, it neutralizes 1 of the HCl's, but you still have a lot of HCl floating around, you still have a lot of H+ ions floating around, and so the indicator still shows that it's colorless because the solution is overall acidic still. So you continue on with the titration, adding more and more and more base until finally you get to the point where all of the acid is pretty much neutralized except for 1 left. So long as you have acid floating around, even if there's not a lot, the solution is still acidic and the indicator remains colorless. By adding the last base, I have neutralized all my acids and my solution is considered to be neutral. This is known as the equivalence point, where the mole of acid and the mole of base are stoichiometrically equal. So there's no more sodium hydroxide, no more hydrochloric acid, just the salt and the water produced during this neutralization reaction. The solution now has a neutral pH. However, it is unlikely that you'll ever be able to stop the titration at the equivalence point. To be able to match up each molecule of sodium hydroxide with one HCl perfectly and having nothing left over or in excess is very, very, very unlikely. Each droplet of sodium hydroxide from your burette contains quadrillions of quadrillions of quadrillions of hydroxide ions, so it's very, very difficult to precisely react molecules on a one-to-one basis. So if the equivalence point is practically impossible to reach, the next best thing is called the end point. That is where the indicator changes color to signify a pH change. So just like in our example, I can't just stop at marble number 6 and that's it. I have to throw in the 7th marble. I have to overshoot the number of holes in order to indicate that every hole has been filled out with a marble. Similarly, I can't just stop at the equivalence point. I have to overshoot it, adding a little extra base to cause my indicator to change pink, or whatever color your indicator may change to. And that's why during a titration, we always ask you to stop once you've reached a very, very faint permanent pink color. A faint pink color indicates that you are weakly basic, so you've only overshot the neutral point by a little bit. Now I can count how many bases I threw inside, 1, 2, 3, 4, 5, 6, 7, and 8 bases, and say that my acids that were originally in my solution was slightly less than 8. If you ended the titration at a very, very dark pink color, then you've made the solution very basic and you added in way too many bases. And at that point, you'd be overestimating how much base you threw in there, and again, overestimating how much acid was originally inside your beaker. It would be like overshooting this with 20 marbles and saying, oh, there must have been 19 more holes inside then. No, we only want one marble to come out, not 19 other marbles to come out. Otherwise, we overestimate the number of holes that were inside that small tunnel, or overestimating how much acid was originally inside my solution before it was neutralized. Alright, so let's do a sample calculation involving the titration of a strong acid with a weak base. In this example, we're going to try to find out what is the concentration of an unknown HCl. We are going to use a sodium hydroxide that we created, so we do know its concentration. So the unknown hydrochloric acid is inside the Erlenmeyer flask, and your known concentration of NaOH is inside the burette itself. Because HCl is a strong acid, it will 100% ionize. You'll see a lot of H+ ions and chlorine ions floating around in solution, making the pH below 7, which is in the acidic range. So when we click the Begin Titration button and add 5 mL of sodium hydroxide, adding in the NaOH will cause you to produce water and also NaCl. So there's your Na ions, and of course Cl ions stay separate because sodium chloride is a salt that dissolves very, very easily, and so it remains in its dissociated state as well. Although we added some sodium hydroxide to our solution, it still remains acidic because not enough of the H+ ions were neutralized. So if we add another 5 mL, again we neutralize more of the H+ ions, creating more water, more sodium chloride in its dissociated state, but not enough, so the pH still remains below 7. But you do realize the pH is still increasing. The solution is less acidic, but becoming a little more basic. We continue by adding more sodium hydroxide. Again, more water molecules are formed, more NaCl is formed. Add another bit of NaOH, and again, more water, more NaCl is formed, but we still have H+ ions flowing around, so therefore our pH is still going to be below 7, it's still in the acidic range. I'm going to continue adding more NaOH, and the moment we neutralize the last 2 HCl's, the pH skyrockets to a pH of 7, because pH 7 means you're completely neutral, you have no more acid, no more base, it's just water and the salt floating around, which is the case we have here. This is known as the equivalence point, but as I mentioned earlier, the equivalence point is practically impossible to reach. It's just not likely for you to be able to react HCl and NaOH on a one-to-one basis. So more than likely, you will overshoot the equivalence point by just a little bit, hopefully, making your solution basic, and therefore changing your indicator to a light pink color. We can then record how much sodium hydroxide you used to neutralize all the HCl in there. And now you have the concentration of the NaOH, as well as the volume of the NaOH used. Allows you to rearrange this equation so that you can find the moles of NaOH you threw into the Erlenmeyer flask. Since it's a 1-to-1 ratio, for every 1 sodium hydroxide you neutralize 1 HCl, therefore you have the moles of HCl. Now, during the titration, you chose how much HCl you poured into the Erlenmeyer flask originally for each trial. So you also have this value over here. Since concentration is equal to moles divided by volume, and you have those two numbers, you've now found the concentration of your unknown HCl sample. So at the equivalence point, there's no more acid, there's no more base, neither of these can affect the pH anymore because they're not present. We also don't have to worry about the salt that's produced during a strong acid, strong base titration because take a look at this. Sodium chloride breaks up into sodium and chlorine. Sodium, you can try to react with water, but you make a strong base. And we know that strong bases cannot stick together, so this reaction does not occur. Similarly, HCl is a strong acid. It doesn't stick together, it completely dissociates or ionizes rather. It too will break up. Therefore, neither the sodium nor the chlorine will affect the pH. We call them spectators. All right, so really, the only thing that will affect the pH now is just water. And because water has a pH of 7, therefore the equivalence point for strong acid, strong base titrations is a pH of 7. Now let's see what happens when we titrate a weak acid with a strong base. Let's take, for instance, acetic acid will be our weak acid, sodium hydroxide will be our strong base. During this neutralization, we create the salt, which will be sodium acetate, and water. Now at the equivalence point, you'll have no more acid, no more base, because they have been completely neutralized. You will instead be left with salt and water. Now these salts are typically strong electrolytes. We can check our KSP chart to make sure they are not present, and sodium acetate is not here, so we can assume that 100% dissociates into its ions sodium and acetate. And we can check to see if these ions will undergo salt hydrolysis. With sodium ions reacting with water, you make H plus NaOH. We know NaOH is a strong base, so that's not allowed to happen. So that would have no effect, so sodium would be my spectator. However, the acetate ion over here, reacting with water, would make a hydroxide ion and CH3COH. CH3COH is our weak acid, and we know that weak acids do not ionize completely, so it will stay stuck together for the most part in its molecular form. That means there will be hydroxide ions floating around solution. If there's a hydroxide ion floating around solution, that means my pH will be slightly basic at the equivalence point. So unlike the equivalence point at a strong acid, strong base titration where the pH is equal to 7, your equivalence point for a weak acid, strong base titration will be slightly basic, and that is due to the salt hydrolysis of the salt you produce, leaving you with hydroxide ions left over into your solution. The opposite is true for weak base, strong acid titrations. Let's take a look at this example over here. Aluminum hydroxide will be our weak base because it's a group 3 hydroxide. Only group 1 and 2 hydroxides are strong. Hydrochloric acid is our strong acid. And then it'll produce aluminum chloride salts and water. Once again, at the equivalence point, you should have no base left over, no acid left over because they have both been neutralized. You'll only have salt and water. Checking our solubility chart, I don't see aluminum chloride there, so I can assume it 100% dissolves or dissociates, releasing aluminum ions and chlorine ions. I can then check the individual ions to see if they'll undergo salt hydrolysis to react with water. Looking at the aluminum, through a single displacement reaction, it makes aluminum hydroxide and H plus ions pop out. Aluminum hydroxide is a weak base, so I know it will stick together, and that means the H plus ions will be allowed to float around. With chlorine, on the other hand, when it undergoes salt hydrolysis, you get OH minus being released and HCl being formed. But of course, HCl is a strong acid. That can't form, that can't stick together, so this side has no reaction, making my chlorine anion a spectator, while the aluminum results in the formation of H plus ions. So because H plus ions are floating around, my solution is going to be slightly acidic. And there you have it, a slightly acidic equivalence point for the titration of a weak base in a strong acid. Now, one other characteristic we need to look at is the presence of a buffer region when it comes to weak base, strong acid titrations. Weak acid, strong base titrations also have a buffer region, but when it comes to strong acid, strong base titrations, there is no buffer region. If you recall, a buffer minimizes pH changes, so it prevents the pH from changing too drastically in either direction. Now, if you recall, hydrochloric acid is a strong acid, so 100% breaks up. So if I had 5 HCl molecules, all 5 of them would break up and dissociate into H plus ions. So if I was calculating my pH for this situation over here, it'd be the pH of the negative log, and the concentration of H plus would be based on 5 of these H plus ions. Now, if I added a base to my solution, it would neutralize one of the H's, and now it'd be based on a pH of 4. If I add another base, it'd neutralize another over here, and now be based on pH of 3 of the H pluses. Neutralize another one, then you got 2, neutralize another one, now you're only left with 1, neutralize this one, Now you're at the equivalence point. There's no more acid, no more base. Weak acids, on the other hand, do not completely ionize. Less than 1% will release their acetate ion and the H+ ion. So if I had 5 acetic acid molecules, only 1 H+ would have been released. So my calculation for pH is based on just 1 H+ ion floating around. And if I were to add a base to neutralize that H+ ion, this acetic acid molecule would then release its H+ ion. But these guys would not, down here, they would not release their H+, and therefore my pH calculation is still based on just 1 H+ ion there. Now if I neutralize this one, then this guy will release its H+, and again, I am only releasing just 1 H+. And if I neutralize this one, again, my calculation is based on just 1. And if I neutralize this one, my pH calculation again is just based off of 1. Until finally I neutralize this one, and now I've reached the equivalence point. And that is why weak acids and weak bases have a buffer region where the pH doesn't change much. So while strong acids, strong bases, you can definitely see the change in pH as you are titrating. With weak acids and weak bases, that concentration remains fairly consistent because they don't release all their H all at once, whereas strong acids, strong bases do release all their ions all at once. Alright, so weak acids and weak base titrations have a region where the pH will not change too much. We call that the buffer region. Alright, buffer region. Whereas strong acids, strong bases, they have no such buffer region because all of their ions are released all at once, and we do see the change in H+ concentration with each drop of sodium hydroxide or whatever base you happen to be titrating it with. Alright, so let's do a sample titration calculation. In this case, we are titrating a weak acid against a strong base. So 25 milliliters of 0.1000 molar acetic acid is titrated against 0.1000 molar sodium hydroxide. Part A asks, what is the solution pH when 10 milliliters of sodium hydroxide is added? Now the first thing I'm going to do is I'm going to try to find out the number of moles of each substance involved. And you'll notice this is not an ice chart. I'm not measuring in moles per liter the concentration of each substance, at least not yet. Because during a titration, the volume is going to change. So you initially had 25 milliliters of the acetic acid, but to that you're going to add 10 milliliters of the sodium hydroxide. So with a new volume, you're going to have a new concentration. And before you can calculate that concentration, we need to know what the mole values are for each. So if you recall, moles is equal to C times V, concentration times the volume. So the mole of the CH3COH is equal to the concentration, which was 0.1000 molar, the original concentration, times the original volume, 25 milliliters. Don't forget to convert into liters. And then we can plug that in as 2.5 times 10 to the power negative 3 moles of acetic acid. Do the same thing for the sodium hydroxide. The original concentration was 0.1000 molar. We have 10 milliliters of the sodium hydroxide being added, and thus, we have the 1.000 times 10 to the power negative 3 moles of sodium hydroxide present. Since the stoichiometric ratios between acetic acid and sodium hydroxide are 1 to 1, therefore 1 times 10 to the power negative 3 sodium hydroxides should react with 1 times 10 to the power negative 3 moles of acetic acid. Thus, sodium hydroxide will be my limiting reagent. It will run out first, and so I'll use it all up. There will be none of the sodium hydroxide left. Since it's a 1-to-1 ratio, I'm going to use up the same amount of acetic acid. That means acetic acid will be my excess reagent. I'll have some of it left over, so 2.5 times 10 to the power negative 3, and I've used up 1 times 10 to the power negative 3. That leaves me with 1.5 times 10 to the power negative 3 moles of acetic acid left over. And of course, it's also a 1-to-1-to-1 ratio of the sodium acetate. So I will produce 1 times 10 to the power negative 3 moles of the sodium acetate salt. You'll notice that I didn't include water in my calculations. Because it's a pure liquid, it doesn't affect my equilibrium expressions, so I'm not going to worry about it. Now that I have the number of moles of the acetic acid and the sodium acetate, I can calculate their new concentrations. This new concentration, of course, is due to the new solution volume of 35 milliliters. Alright, so the 35 milliliters came from back here, 25 milliliters of the 1000 molar acetic acid, and the 10 milliliters of the sodium hydroxide, so 10 mils plus 25 mils adds up to 35 milliliters in total. So my new concentration is equal to moles divided by volume. It comes out to 4.29 times 10 to the power negative 2 moles per liter of acetic acid. And same thing over here with the acetate or sodium acetate, 1 times 10 to the power negative 3 moles of that over the new volume of 0.035 liters gives me 2.86 times 10 to the power negative 2 moles per liter. Now you may also notice that I'm only worrying about the acetate ion. I don't care about the sodium component of sodium acetate. I just worry about the acetate component because the sodium is going to be a spectator ion, as we've seen before. Only the acetate ion will participate in the common ion effect, which will in turn prevent my acetic acid from releasing as much H+ ions as it normally would. And that of course would affect my pH, which is what we'll be calculating next. Now let's take a look at this. I have leftover acetic acid, but no more sodium hydroxide. It was our limiting reagent. It's all gone. So the NaOH has no effect on my solution pH anymore. I do have acetic acid. That is going to affect my pH because, well, the acid is going to release H+ ions. So I'm going to set up an ice chart for the ionization of acetic acid to see how much H+ it will release, and then from there calculate my solution pH. So I'm going to take the amount of acetic acid I have left over after the sodium hydroxide had neutralized it. This is how much acetic acid I had left over, and punch it in over here. And then, because of the common ion effect and its interference, I'm going to take how much acetate ions are floating around in solution that were created during this neutralization process, and punch it in over here. Since the reaction can't go in reverse because there is 0 H+ ions released so far, we have to go forward. That means this is going to be a minus X, plus X, and a plus X. It's all 1 to 1 to 1 ratio. And that leaves me with an equilibrium value as written over here. I can then punch these values into my Ka expression. To simplify my calculations, I'm going to use the approximation rule. So again, take the Ka value, take the concentration value, initial concentration value, divided by the Ka value, which was given to you in the question. And if it's greater than or equal to 1,000, then X is negligible. And of course, when I did the calculations, I found that X was negligible, which means I can just simplify the calculations by putting in 4.29 10 to the power negative 2 and 2.86 times 10 to the power negative 2. And I don't have to worry about the quadratic equation from there. When we solve for X, you'll get 2.69 times 10 to the power negative 5 moles per liter. And since X also represents the hydronium concentration, I can then punch it into my pH calculation. From there, we get a pH of 4.57. Now let's double check to make sure that this answer makes sense. 4.57 is below 7, so therefore this is in the acidic range. If I look back at my previous examples over here, I have no more base, but I do have leftover acid, so therefore my solution should have an acidic value, and that is correct. So everything seems to check out. Now part B of the question asks, what is the pH of the solution if you add 25 milliliters of the sodium hydroxide now? So just to keep track, we have 25 milliliters of sodium hydroxide, 25 milliliters of the acetic acid, so in total I have now 50 milliliters, that's the new solution volume. So again, because of the new solution volume, I'm going to have a new concentration. To calculate the new concentration, I'm going to require the moles of each component in order to find out how this new volume has affected its new concentration. So using the equation moles equal to C times V, I was able to find out the moles of acetic acid and the moles of sodium hydroxide. You'll notice that they are identical. And since this ratio is 1 to 1, where 1 sodium hydroxide neutralizes 1 acetic acid, well, 2.5 10 to the power negative 3 moles of NaOH would neutralize 2.5 times 10 to the power negative 3 moles of acetic acid. And that means you'll have 0 acetic acid in your solution, and you have 0 sodium hydroxide in your solution. When there's no more acid and no more base, you've reached the equivalence point, where only salt and water remain in our solution. So without any acid to affect my pH, without any base to affect my pH, the only thing that could potentially affect my pH at this point is the salt that was produced. So I'm going to use this value and find out what the new concentration of my salt is going to be. So again, the 25 mils of the acetic acid, 25 mils of the sodium hydroxide together make 0.050 liters. Take this value over here, moles divided by volume, and you now have the new concentration of just the salt. Again, I'm not going to worry about the sodium ion from the sodium acetate. It's going to act as a spectator ion. However, the acetate ion can react with water to form acetic acid and hydroxide ions. So that means my solution will have some hydroxide ions floating around at the end, thereby affecting my solution pH, my final solution pH. So I'm going to set up an ice chart to see how well the acetate ion will undergo salt hydrolysis, reacting with the water to release acetic acid and also the hydroxide ion. Initially, we calculate 0.05 moles per liter of acetate ions floating around. So that was from the previous slide over here. And there is no more acetic acid because remember back here, the acetic acid was all neutralized by the sodium hydroxide. So we're going to create some new ones, but there's going to be none to start off and no hydroxides have been released either. So the reaction has to go forward. It can't go in reverse. So therefore, it's a minus X value, plus X value, and a plus X value because everything is a 1 to 1 to 1 to 1 ratio. Thus, my equilibrium values will be 0.05 minus X, an X, and another X. Now, in the original question, we gave you the Ka value for acetic acid, which is 1.8 times 10 to the power negative 5, but the acetic acid is not the one that's providing the H plus or the OH minus ions right now to affect my pH. It's the acetate, its conjugate base. So because the acetate is a conjugate base, we need to calculate the Kb value. So remember, this is a common mistake a lot of students make. They will try to use the expression using Ka only because the Ka was provided to them in the original question, and they are not thinking about whether it's an acid or a base. Okay, so because it's a base, we're going to use Kb. Don't forget to convert from Ka to Kb. We use the equation Ka times Kb equals to Kw, and Kw, of course, is 1 times 10 to the power negative 14. So to convert, we're going to rearrange the equation. Kb is equal to Kw over Ka, and get 5.56 times 10 to the power negative 10. Now I can write out my equilibrium expression for this base and how well it will react with the water molecule to produce these compounds over here. So products over reactants, acetic acid hydroxide over the acetate ion. I'm going to substitute the numbers in. Again, I'm going to use the approximation rule, so I'm going to take the initial concentration divided by the Kb value, and it's going to be greater than or equal to 1,000. Therefore, the X value is negligible, and I can just substitute this one in here, and it makes my calculations so much easier, and I can solve for X. Now, since X represents the hydroxide concentration, I have to calculate the pOH first. pOH, negative logarithm, the hydroxide concentration gives you 5.28. From there, I can rearrange the pH plus pOH conversion equation. It equals to 14. And rearrange the equation and get 8.72. As a double check, we saw that a weak acid titration with a strong base results in an equivalence point, slightly basic, and that is exactly what we have over here, 8.72. Now be careful, a lot of students goof this one up. Another common mistake I see students make is in memorizing these equations incorrectly. Sometimes I'll see students write down Ka plus Kb is equal to 1 times 10 to the power negative 14, or worse, I might even see them say Ka plus Kb is equal to 14 itself. Or I might see pH times pOH equals to 14, or the worst part, pH times pOH is equal to 1.0 times 10 to the power negative 14. So just be careful and make sure you memorize these equations correctly. Alright, so what I would like you to do now is try out the practice worksheet over here. The numerical answers are bolded on the right hand side. Full solutions can be found on our course Moodle. If you have any other questions, let me know.